Welcome everybody to this technical seminar from the Biofactory Competence Center in partnership with T Technology on the topic Monitoring Microbial Growth using Variable Path Length Spectroscopy. My name is Tanja Buch and I'm the Technical Director of the BCC in Switzerland. To start with, I would like to say a couple words to myself. I'm holding a master's degree in Bioprocess System Engineering from the University and Max Planck Institution in Magdeburg in east of Germany. After gaining some industrial experience in Switzerland, I continued my studies in Ireland at the Dublin City University, where I completed my PhD in Bioprocess Engineering on an industrial project in cooperation with the company MSD. Throughout my time in Ireland, I was involved in several industrial projects, as well as a trainer at the Training and Research Centre Nibert in the south of Dublin. Here I developed and delivered applied training courses to the entire biopharma sectors in Ireland. In 2015, I decided to follow my colleague Ian Marison back to Switzerland and helped him to develop and set up the Biofactory Competence Center in and since 2016, we are operational in providing training and research services to the biopharma industry. This brings me to my second introduction here. What actually is the BCC? So the BCC is a non-for-profit organization supported by the cantonal government in Fribourg with the aim to support the pharma and biopharma market and industry in Switzerland and also abroad. For this, we have three main activities. Our main activity is the provision of training courses, which we give to the biopharma sectors. For this, we have constructed a GMP-like facility in our plant in Fribourg. These are not meant to operate as a GMP factory, but we try to simulate them as much as possible to a GMP process. In these labs, we can provide training courses on all different aspects of a biopharma process, starting from seed train development over USP processes, down to cell separation and all the way to product purification on filtration or chromatographic technologies. For this, we also have two different USP suites, one for mammalian processes and the other one to cover microbial processes. Our training can be adapted to all different levels, for example, for operators or even cross-training courses, where we train people on GMP principles, how to behave in clean rooms, or how to work in an aseptic manner. We also give more expert training courses, for example, on continuous processing in fermentation or cell culture processes, but also on very technical steps, for example, in continuous chromatography. We give these training courses in three different languages, since Fribourg is right at the language barrier between French and German. We provide these courses in either English, French, or German. The duration of these training courses can also differ between 1 day and up to 6 weeks, completely what the client requires for the training courses. Our second activity of the BCC is the provision of technical service to the biopharma industry. Here we try to support the industry in process development or process optimization of key steps and try to find solutions how they can overcome these challenges in their processes. Another part of the technical service is also the development or optimization of analytical methods, which become more and more important in monitoring and control of your processes. We usually have an internal joke in our company which says, just ask. So meaning, if you have a problem in your process, just approach us and either we can help you or we try to find a solution for you with one of our collaborators. Our last and third activity is the design of modular and flexible facilities, which can be used either for training, research, or also for production. And here we finally kicked off this process with a contract that we signed end of last year, where a local pharma company in Fribourg decided to extend their production facility and wanted to build a new plant with over 1,000 square meters. and they decided to go ahead with our modular design, which should be finished and operational by mid of next year. You may ask yourself how the collaboration between the BCC and C technology originated. In 2018, one of our clients that we gave training courses for approached us because they heard about the variable path length technology and they wanted to have this technology implemented in their training programs that we gave to them. Since at that time, we didn't have such technology available in our labs, we approached the technology and asked them if they would be interested to collaborate with us and to support us with one of their systems so that we can implement it in our training programs, but also offer it as services to our clients. And C technology liked our ideas and they gave us first the SoloVPE system, because that time we had a very high focus and demand on continuous DSP. And the SoloVPE system is a brilliant tool in order to include it as a monitoring and control tool in protein concentration throughout your continuous purification process. And in our training courses, we implemented it, for example, after a single pass TFF system in order to follow the protein concentration in real time and to see, do we really have a consistent protein concentration coming off this filtration cassette, or does it vary over time? We also implemented the flow prior to a continuous chromatography device, here not as a monitoring system, but more as a control device in order to control the protein load onto the columns and to avoid overloading your columns throughout the continuous process. Since this collaboration worked really well, C Technology decided to also provide us with their benchtop device, the SoloVPE system. And having this benchtop device now in our labs, we could even go one step further and we could think, what alternative application can we use the variable path length technology for? And one of the first technologies that came to mind was measuring the cell growth of microbial processes. As you probably know, usually we are using a standard spectrophotometer and follow the cell growth with an absorbance of 600 nanometers for E. coli cells, but you always have to dilute your samples already at the very early stage of the process. So we thought, why not try to adapt this variable path length technology and eliminate this dilution step from our process and therefore become a higher accuracy in our measurement and a new tool in order to monitor and ideally also control our microbial processes. You may think now, what does microbial fermentation have to do with gene therapy and viral vector production? But as you know, you always require a certain amount of plasmids in order to deliver the transgene or also the plasmids that encode for our viral particles into our mammalian cells or insect cells for the viral vector manufacturing process. And these plasmids are actually produced with a microbial process, in most of the cases with an E. coli fermentation. And since the demand and the interest in viral vector therapies is increasing over the last years extremely, there's also a really high need for large-scale production of plasmids. And therefore, we require efficient E. coli fermentations, and the variable path length spectroscopy technology can nicely be adapted and implemented in order to monitor, but ideally also control the cell growth of our E. coli cells throughout the USP part of the plasmid production part. And this is why we cover this here today. So just to recall before we go into all these details, why monitoring and control is so essential. As we all know, cell concentrations and cell growth are one of the important critical process parameters which have a significant impact on the critical quality attributes of our products. And regulatory agencies such as the FDA or also the EMA expect more and more good process understanding and process control, which we can only provide if we have good analytical methods. So to give you one example, when we talk about fermentation processes, we always usually separate them in two different phases. The first phase being the cell growth part and the second phase being the product production part. And the different phases are divided with an induction time point, which can be dependent on a temperature shift or also on a substrate shift in order to change the metabolism. But in most cases, they are dependent on the cell concentration present in our bioreactor at this given time point. So if we look at our lower right-hand image here in this graph, and we, for example, identified that the ideal time point for the induction is at an OD of 0.5, we see it's right in the middle between two sampling time points. So when we took a sample after 90 minutes, we have only an OD of 0.4. So we have to make the decision now, do we induce already now in order to start the production of our product, or do we wait until the next time point? If we start the induction too early, it means we don't have enough cells present, and lower cell number means we are also consequently producing less product. However, if we wait 30 minutes until we take the next sample and then we have an OD of 0.6, we see here already we are out of the exponential phase going into steady state, which means the metabolism is slowing down. Some of the cells may go in apoptosis, and this can lead either to inefficient product formation or some product may not have the same quality as we need it to have. So therefore, if we have reliable and good accurate methods, can definitely be improvement in monitoring and controlling our microbial growth process. So let's look at the current technologies that we have available in order to monitor the microbial growth. The most method, it's probably the offline method using a standard spectrophotometer and measuring the optical density of our cell solution at different wavelengths depending on the cell line. For E. coli, for example, at 600 nanometers. However, the drawback here is that this linear relationship from a standard spectrophotometer between the optical density and our cell concentration is only up to an OD of 0.5, meaning all our fermentation samples that exceed the OD of 0.5 need to be diluted, which we can also see in this little graph on the lower and left side corner, where we see in blue our optical densities without making any dilutions, even though the cutoff of 0.5 is reached. In green, we see the example where dilutions have been made prior to the optical density measurement. And as we can see, after the cutoff of 0.5, we see already a clear distance between the measurement without and with the dilution. And this is getting more and more significant as long as the process lasts. So this clearly shows after the cutoff of 0.5, we just have to make dilutions for this step. But let's look what do we have for online method nowadays available. Currently, the push goes into photometric sensors, for example, the optical probes from Mettler Toledo, which become more and more interest in industry and also are started to be applied by a lot of different industrial companies because they have good accuracy and they also are robust over a certain time of the fermentation process. However, also these optical probes have some drawbacks. First of all, they have their limitations with high cell density cultures, and they have the tendency of material buildup around the sensor, especially on the optical lens at the bottom. In addition, if you require a lot of oxygen and you need a high aeration rate, these bubbles can also interfere with our measurement. But one of the biggest drawbacks of these optical probes are that we are not measuring one specific point, but we are always measuring a spectrum at each given time point when we have to measure our cell density. And if you measure a spectrum, you need to do chemometrics models in order to convert the spectrum into one real given data time point, which can be equivalent to the optical density value. And these can be time consuming and also needs a certain expertise in order to develop these models. So we see there is definitely room for an alternative method and also for an improved method as offline, but also for online methods in order to follow the microbial growth in our bioreactors. So let's have a quick look how the variable path length technology works. You probably all know the principle of a standard spectrophotometer, which follows the Baird-Lambert law, where we say our absorbance equals the extinction coefficient times the concentration of our solution times the path length. Path length meaning the distance of the light that it has to travel through in order to measure the absorbance. The path length in a standard spectrophotometer is always set to 1 centimeter due to the shape of our cuvettes, but also due to all the standard spectrophotometers, which allow only a 1 centimeter path length in the measurement. So meaning with the extinction coefficient being a constant, the absorbance equals the concentration. A nice linear relation, and this would be great. However, the problem here again is that this linear relation is only linear up to an absorbance value of 1.5 or maybe 2, depending on what we are measuring. So as soon as we have a high concentration of our product that we want to measure, we have to dilute again our sample to reduce the absorbance below 1.5 to work in our linear range, and that the Baird-Lambert law is actually valid. So see, technology here was very smart. They thought, what other opportunity do I have in order to reduce my absorbance value below 1.5, but without the need of diluting my sample? And of course, the only parameter left in my equation is the path length. So meaning if we reduce the path length a lot when we have a high concentration, we can reduce our absorbance below this famous cutoff at 1.5. So we are in the linear working range, but we didn't need to dilute our sample. This is also the machine now that we can see here on the upper right-hand side. We have a standard spectrophotometer, which is working here as a light source. And then we have the SoloVPE system on the top, where we see the light source is connected with the fiber optic cable to the top of the system and goes all the way down to the nozzle. And at this little nozzle, we can implement a fibrate, and the fibrate afterwards can go down into the liquid and is the extension for the light source. Our cuvettes are placed here on this little plate holder, and our detector is now on the bottom. So if we zoom in for our cuvettes, what we see down here, we have the cuvette with the process sample, the detector would be at the bottom, and our famous path length is defined from the bottom where the detector is all the way up to the end of our fibrate, which is the extension of the light source. And this fibrate can be moved up and down in very specific step paths so that we can adapt the path length according to the concentration so that our absorbance is always below the cutoff of 1.5. Question now may be, how do we know what path lengths to choose if we don't know the concentration? Very good question. And the answer here is what the SoloVPE system is doing at the beginning. It scans through our unknown process sample all the different path lengths from the bottom to the top in order to find the path lengths where we have an absorbance value of 1.0. Because we know if we work around an absorbance of 1.0, we are definitely in the linear range of our Baird-Lambert law. So we see this here on the right-hand side. The starting path length always starts at an absorbance of 1.0 usually. But instead of just having a one-point measurement, we want to improve our precision of this measurement, and we are actually measuring 10 data points instead of just one. So we are starting with a path length of 1.0, but then we measure 9 further ones with a stepwise path length depending on the starting path length. And also the step path length is dependent on our protein concentration. So meaning if we have a high protein or product concentration in our solution, we have, of course, a very narrow starting path length in order to have the absorbance down at 1.0, but the step path length is actually very narrow as well, so around 0.05 millimeters. However, if we have a low concentration present in our product or protein in the solution, the starting path length is quite high up, probably close to 1 centimeter, but the step path length is now at 0.15 millimeters. And then what the system is doing, we are plotting the absorbance over the path length, and the relation should definitely be linear, defined by the Beer-Lambert law. And the slope out of this, which we also often call the slope absorbance, should have an R-square of at least 0.999 in order to give us confidence that this measurement works. And the slope absorbance can then be recalculated to determine the concentration value. This is how the SoloVPE system works under their default setting, and which works really well in order to determine unknown protein solutions. So we thought, why don't we try exactly the same process steps for our cell growth of our E. coli cultures? And unfortunately, with these settings, it didn't work really well because we had quite a lot of variation between our absorbance and the path length, and the R-square was sometimes below 0.9, and this didn't give us enough confidence that it worked. So we actually went a step back and we thought, what are we actually measuring here? So if you have a protein in solution, the protein is soluble, and you measure the absorbance, which is defined as the ability of a medium to absorb the light. However, when we now look at our cells in our medium, these are more particles, and we are measuring the optical density, which is defined as how much light passing through a medium, which is kind of the opposite a little bit. Plus, if you have a lot of particles in the different layers, the chances of light getting through get slimmer and slimmer. So we thought, okay, why don't we just fix our starting path length? So instead of to having it variable and always starting at an absorbance of 1.0, we decided to fix it to 3 millimeters. And also the step path lengths now, we thought if we do these steps a little bit wider, we are measuring our linear range over a bigger distance, which should improve our linearity. And this is what we did. So we fixed also the step path lengths to 0.15, which is at the end the complete opposite what we did with the protein concentration measurement. But we also measure the difference when we measure the optical density. And we kept our 10 measuring points that we want to measure. So we used these new set points of our method and tried it out in an experimental fermentation with E. coli cells. So what we did, we cultivated E. coli cells in shake flask, 250 milliliter volume, total volume, standard YPG medium at 37 degrees, 150 RPM. And we took samples every 30 minutes and measured those samples with a standard spectrophotometer for the optical density values, but also with the SoloVPE system for the slope absorbance value. And these were the results that we received. So on the left-hand side first, the results from a standard spectrophotometer. We measured optical density, and of course, after this famous cutoff of 0.5 was reached, we had to dilute our samples in order to get this nice growth curve of our E. coli cells as we would expect them. Of course, we also had to include here the blank correction because YPG medium does absorb the light at 600 nanometers, so you have to make the correction in order to avoid interference of the medium with the measurement. We took the same samples and analyzed them with the SoloVPE system for the slope absorbance, what we can see now on the right. And here, there was no need for diluting the samples, and we also didn't include any blank correction due to the YPG medium. And when we compare the growth curve and the trends that we can see between the optical density measurement and the slope absorbance measurement, they look very alike. So this gave us confidence that there definitely is a potential there to use the variable slope spectroscopy to measure the cell growth or to follow the cell growth throughout a microbial fermentation. The next step that we wanted to know is, can we make a correlation between the optical density measurement and our slope absorbance values? So what we did, we took the remaining samples we had left over from our experiment. We concentrated the cells a little bit because beforehand in a shake flask, the maximum OD was only 3, and we wanted to get a little bit higher cell densities. So we concentrated them up to an OD of 25, made several dilutions of those, measured the different samples for optical density with a standard spectrophotometer, but also with the SoloVPE for the slope absorbance, and we plotted these two different values over each other. And as we can see here, we identified a nice linear correlation between the two parameters with an R-square of 0.992 and a correlation factor of 94.5. When we looked at the variability of these measurements, we saw that measuring the slope absorbance of one sample several times resulted in a variability of less than 2%. Using our correlation factor to recalculate it into an optical density value increased the variability a little bit, but was still less than 5%, which is a very good value for an analytical method. So this showed us there is a potential there. So we wanted to have a proof of concept. So we repeated our experiments in a shake flask with E. coli, the same settings than before with YPG medium at 37 degrees. And again, we took samples every 30 minutes and measured those with a standard spectrophotometer for optical density, and then also with the SoloVPE system for the slope absorbance values. And what you see now on the lower right-hand corner is in blue, the values of the standard spectrophotometer, our optical density values. Again, after the cutoff of 0.5 OD was reached, we had to dilute them, and we had to include the blank correction of the interference of our medium samples. But the growth curve was almost as expected in what we saw before, with some small deviations here around a processing time of 4 and 4.5 hours, which we probably assume that this is due to some dilutions errors that was made by the person who performed this experiment. However, we took these same samples, analyzed the slope absorbance with the SoloVPE system, and then we used our identified correlation factor in order to recalculate the slope absorbance into optical density values, and we plotted these results in the same graph and can be seen as the green dots. And as you see, they follow exactly the same trends than what we identified with the standard spectrophotometer, except our little deviation that we see here, where we assumed this might be due to the dilution errors, because with the SoloVPE system, we don't need dilutions, and therefore we don't have this variability in these measurements. So these results, again, convinced us that it's definitely possible to use the variable path length spectroscopy technology in order to implement it as a monitoring tool for microbial processes, especially with E. coli cells, as we can see it here. But the overall aim was to actually not have another offline method, but the idea also is to have ideally an online method, which we can not just use for monitoring, but ideally also as a control tool in order to run our microbial processes more efficiently. So one of our next steps that we are planning on doing is to try to implement the SoloVPE system to one of our benchtop bioreactors with a pump. We are circulating our process sample through the bioreactor with a pump to our SoloVPE system and then back to the bioreactor. And this should allow us to have an add-line tool with recirculation loop in order to monitor the cell growth in real time and use the SoloVPE data in order to control the feed that we have to start, or maybe identify the optimal induction time point in order to shift from the cell growth part to the production part of our product in our fermentation setup. With this, I'm at the end of this technical seminar, and I'm more than happy to answer any questions you may have on this topic. Thank you very much for attending, and if you have follow-up questions also later on, please feel free to contact us or C Technology directly in order to help and support you if you want to implement this method in your microbial process.